the standard state is the thing that we indicate with the sort of superscript circle. Occasionally, you also see it as the circle with the line through it. Dr. Deckert has sort of said, oh, okay, circle is sometimes used as ideal pure substances. I'm going to just say that in this class, I will use the circle to indicate standard state and the star to indicate pure substance. There happens to be a bunch of different nomenclatures for this. This is one that I'm going to stick with. So for a standard state, right, we can say what the standard state is for each type of substance. Right? For a gas, the standard state is 1 bar of pressure of that glass, and we say that the gas is ideal. For a liquid or solid, we say that it is under a 1 bar external pressure. We don't really worry about what the thing that's applying the pressure is. We're not paying attention to that. We're thinking about the chemical potential of the liquid or the solid. For a liquid, for a solute in solution, our standard state is 1 mole per liter, and we assume that it is an ideal solution. And we can correct based on changes in that. All right, so I will quickly go through that derivation for the chemical potential under non-standard pressures, though I did this in class and it seemed like that was mostly okay. I'm going to present it in a slightly different way than I presented the first time, which is, right, if I think about the chemical potential as being kind of like a molar version of the Gibbs free energy, then I can write it a little bit like this, right? The chemical potential of a pure substance looks like molar volume times infinitesimal in P, like d mu. A small change in my chemical potential, it can correspond to a change in my temperature, change in my pressure. And if I want to know what the chemical potential is of a pure substance, so I guess we'll go ahead and we'll add those stars there to remind ourselves that we're thinking about pure substances. The chemical potential of that pure substance at some new pressure P is going to equal the chemical potential of that substance under standard conditions plus some integral from my standard pressure to that other pressure of the derivative of chemical potential with respect to pressure times dP. We'll keep T constant over that process. Right? This is very similar to things that you did in Learning Target 2.3, 2.4, 2.5, where we can calculate a change in chemical potential or a change in enthalpy or a change in energy relative to a derivative, taking a derivative and integrating it. Luckily, I can say, well, d mu dP, I know what that is. I can look up above, and the derivative of chemical potential with respect to pressure is V. So really, what this is this integral. And then if I assume an ideal gas, then V bar equals RT on P, and therefore the chemical potential of my pure substance at some pressure is the chemical potential under standard state plus RT ln P on P naught. If I assume that this is something incompressible, then I get something similar, where now I have V bar times P minus P So far, so good. Right? My solid and my gas above and my liquid below. Now, if I want to talk about a phase equilibrium, I know that the chemical potential of my liquid phase will equal the chemical potential of my vapor or gas phase. Okay, so we got to about here, and then I got a little bit tripped up in class. So let's talk a little bit about why we can basically ignore this piece here. Let's use some example numbers just to justify this. If I want to know how the chemical potential of my liquid changes when I go from standard conditions to some non-standard pressure, and what I'm really asking is for the change in chemical potential of my liquid, which is going to be the chemical potential at some pressure P minus the chemical potential at standard conditions. Well, mu at P, we saw above, is mu sub L, or the mu of the liquid, plus this bit. So those two mu liquids cancel out. So the change in my chemical potential is really just this term here. The molar volume of water, just to get us there real quick, the density of water is 1 gram per milliliter, or 1,000 grams per liter. The molar mass of water is 18 grams per mole. If I do the molar mass divided by the density, then I get 0.018 liters per mole, which is my molar volume. So this change in chemical potential is 0.018 liters per mole times 2 bar minus 1 bar. Let's say we're going from 1 bar of pressure to 2 bar of pressure. And then remember that if we want to convert this into joules, we'll use our 100 joules is a liter bar. That gets us 1.8 joules per mole. So the chemical potential of my liquid increases by 1.8 joules per mole when I double the pressure, from standard pressure to 2 bar. The change in chemical potential for my vapor is the chemical potential for the pure vapor plus RT ln of P on P naught minus the chemical potential of the vapor. And just like before, those things cancel out. So the only difference is associated with this RT term. If I plug in 8.314 joules per mole Kelvin, 298 Kelvin, and those same sets of pressures, I get 1717 joules per mole. Right? So if we're thinking about this versus this, the former doesn't matter at all. And so this is why I got a little bit tripped up, is yes, this is a correct statement, equating the two chemical potentials. But for most purposes, we can ignore the change in chemical potential associated with the change in pressure. Phrased another way, the chemical potential of my liquid at some pressure P is effectively equal to the chemical potential of my liquid at standard state. With this now settled, we can get to what we had set out to derive, namely that the chemical potential of my liquid is equal to the chemical potential of my vapor plus RT ln of P on P naught. That's it. Finally, let's talk through the approach to addressing a problem like this one from your worksheet. So we have now a situation that is a little bit different from what we have encountered before in the example before, where now I have a salt solution. We're not talking about a pure liquid anymore. But I could begin by saying that in order for these two things to be in equilibrium with one another, the chemical potential of my liquid water must equal the chemical potential of my vapor phase water. And this, at the very least, is a pure substance. Right? There is salt in the water, yes, but the gas, the water vapor, doesn't have any salt in it. The boiling point of salt is, I don't know, over 1,000 degrees. So we're definitely not going to have any gas phase salt in the air. We know the right-hand side. Hopefully, you're getting pretty familiar with writing out something like that. What is the chemical potential of the liquid, however? Well, that we can relate to the pure liquid plus a correcting factor for the mole fraction of the water. Right? The chemical potential of my salt solution is going to be the chemical potential of pure water plus some correction due to the fact that we don't actually have pure water. So let's think a little bit about the values of these things. Right? The mole fraction of H2O is going to be probably close to, but a little less than 1. And the natural log of something that's a little less than 1 is a negative value. And so the chemical potential of my liquid water is going to be, of the liquid water in my salt solution is going to be a little lower than the chemical potential of my pure water. If I now combine these two expressions, I can say that the chemical potential on the liquid side is this. It's equal to the chemical potential on the vapor side. And now let's think about what has to happen here in order for these things to be in equilibrium with one another. I've said that this has gotten smaller as a result of the water being not a pure substance anymore. So as a consequence, this will have needed to have gotten smaller as well. We're not going to change the chemical potential of my vapor under its standard state. That's a constant. So what will have to have changed is that RTLN term will have to be a little more negative. And the only way that we can do that is if this term must drop. So the effect of us adding salt is that it reduces the vapor pressure of the water. This is very similar to our negative deviation type mixtures, right? The addition of the salt to the solution reduces the chemical potential. There's an attraction between the water molecules and the salt that is in solution. Those intermolecular forces are strong, and the result is that less water enters the vapor phase.